less popular. Okay. Cool. Now, let me get my slides. Amazing. So we're going to see an example of, today we're going to work on supervised learning, okay? So supervised learning is, for instance, when we're teaching the computer how to perform a task by telling him, okay, for instance, this is the picture of a sandwich. This is not a sandwich, okay? And after showing the computer a lot of pictures of sandwich and not sandwich, we want the computer to start learning how to distinguish a sandwich from a not sandwich. And the idea of supervised is that means basically that we're giving the computer lots of examples from which it can learn from, okay? In this big category that is called supervised learning, we can distinguish two particular scopes, let's say. So we can do classification and we can do regression. So when we need to, for instance, to predict the price of a house, given some data, maybe it could be the number of rooms, it could be the surface area, or the total surface area of the house, then we're talking about regression. So our output is going to be a number that it's the price of the house, that might be between I don't know, $20K to millions of dollars, right? When we want to distinguish something and into discrete classes, for instance, is it a sandwich? Is it a not sandwich? Okay, so we have these two possible states, then that's called classification. And today we're going to see an example of regression, and we're going to see an example of classification. So for instance, we might give the computer the picture of a sandwich. Sure, that's a sandwich. A cat, that's not a sandwich. And maybe in the future, we might show the computer an image, this one. And the computer hopefully is going to recognize if it's a sandwich. I don't know what will happen in this case, but that's why it's important to consider all possibilities. So let's start with linear regression. Let's start with defining our task. Our task is finding the price of a house. So we have some information about houses. So maybe we have, I don't know, a set of 1,000 houses, and for each of these houses we know the number of rooms, the size of the house, the floor number. Right? Top floor house is going to be more expensive than a bottom floor house usually, and then some information about the location, right? Is it inside a city? Is it outside a city? And maybe apart from all this information, we also know the price of the house. Okay, so we're not really predicting because we are given the prices. But the thing is that given this data set, we want to be able, if you give me another house without the price, I want to be able to put a label on the house. Okay, that's worth 300K, for instance. Okay, so as you can see, have some numbers in brackets, 1, 2, ... That means that we're going to have many thousands of these data. Now, this is the model that we want to build. So we have a function that is going to be, maybe complicated. It's going to have lots of parameters that we can change. And given we put as an input the number of rooms, the size of the house, the floor number, and the location, which are our data, as an output, we get the price of the house. Okay, this is just a function. And what we want to do is this. We want to fit the model to the data so that the function gives good estimations of the house prices. Now, this sentence is kind of dodgy. We need to kind of define what it means to fit the model in our data. We need to define what it means to have good estimations of, how do we say that the model is performing good? How do we say that, sure, we did a good job? So this is what we're going to see. In order to try, start simple, let's say that we only have one information about the houses. We have information about the surface area here on the x-axis, and we have the price associated to the house. Okay, so these data, of course, are not actual data. I just made them up, but let's go with the fiction. So each of these red dots represents a data point. Okay, so we have information about the surface area, we have information about the price. And this is the way I label the data, X, Y, and the subscript on top means that it's the first data that we are considering, right? So this is going to be X1, Y1, and this is going to be X2, Y2, for instance. The X is the surface area, as we said, Y is the price of the house, and we want our model given a value of x, to predict a value of the price of the house. Is everything clear so far? Ish. Okay. So the model we're going to choose is quite a simple model. It's the one that you see in the plot as a blue line, and it's just a straight line. Okay. So in this case, we have our value of x. We multiply it with a gradient, and we add a0, which is the intercept with the y-axis, right? And our task basically is fine-tune these parameters a0 and a1 so that our model predicts the data. Now, this may seem as a very simple model. Okay, why should we care? Turns out, a neural network is just basically a spicy linear regression. So again, we see this word, right? We need to find the values of a0 and a1, the best fit the data, right? How do we do that? How do we know if our choice of a0 and a1 are good? We need to find something that is telling the computer, okay, this is a good choice of a0 and a1. This is a bad choice. And this is what the cost function is. Okay, the cost function is a value that tells us if the parameters a0 and a1 are good or bad. So let's see what's the cost function. So here is how we are going to build our cost function. For each of the data, okay, the red dots, we're going to take the distance between the data and our model. Our model is defined once we have a value of a0 and a1, right? Now, what we do now is take this distance, we square it. So this is where the square comes in. And we take the average of all this distance squared, okay? This is going to produce a number. And this number, of course, depends on how is our line, right? How was the gradient of our line, how is shifted is. So generally, I would say that the output of this function is a function of our model A, right? Where A are a0 and a1. So this is our cost function. And we said that no, we want to find the values of a0 and a1 that better fit the data. Now we can be more precise and say that we want to find the values of a0 and a1 that minimize the cost function. Okay, so this process is called training the model. So we want basically to adjust a0 and a1 inside this formula so that C is as small as possible. Okay. Now, this is an example of a cost function. I got the picture from internet. So you could pretend that one of these axes here is a0, and the other axis is a1. Maybe I can even write it. Pen color, red. Maybe not. This is a0. This may be a1. Generally, our cost function is going to be weirdly shaped. Okay, so we might start with an arbitrary choice of a0 and a1, just random. A0 is an A, by the way. A1. That was horrible. Okay, and then we want to find a way to choose to make another guess of our a0 and a1 that kind of gives us a lower cost function. Okay, so for those who are more experienced with calculus, one way could be just take the derivatives of the function c and kind of go in the direction of the derivatives, because that kind of ensures that you are going down and downhill, right? And actually, for a linear model, I would say that's probably the best choice. But instead of going through the maths, I'm just going to say, no, you can choose any algorithm that does that, right? Realistically, most of the times you never implement this kind of optimization process. You always use some of the functions that, for instance, are available in TensorFlow. It's quite natural to implement this thing in TensorFlow. Okay, TensorFlow gives you a lot of very powerful, very complicated algorithms that you don't need to hard code every time. So for the time being, I'm just going to say that you can use any of the available algorithms to find the minimum of this function. Of course, it's not always easy. You can already see here that there is a valley here. So you might go down, you might fall inside the valley. And how do you get out of the valley? That's a very good question. And that's something that a good optimizer should take care of. How to avoid falling into local valleys and how to try and reach the global minimum. Okay. So as you can see, we start with the initial guess of A0 and A1. Then we update our guess, and usually at every update, we get a value of the cost function that is smaller. And that's cool. So basically we're done, right? So yeah, this is another thing that we were talking about. So we said that no, every time we update our values and we go down this black line here. Now we go down in steps. How large is the step? Well, that's another thing that we need to be careful of. If the step is very, very short, it's going to take us a long time to come down to the bottom. Okay. If the step is too high, you may basically overjump your minimum. Okay. You go here and you try. Okay, let's update in this direction, but let's do a lot. Let's update a lot, and you may end up somewhere that is actually farther from the minimum of your cost function. And in this way, you could start jumping around your nicely bowl-shaped function, and you may never reach the minimum. So that's another thing that is important to tune. Usually, when you define your optimizer in TensorFlow, the step size is one of the parameters. And but we're probably going to see this on Saturday during the workshop. So that's cool, but our house is likely not going. The price of our house is not going to depend only on the size of the house, right? There are going to be many more variables. We said the position, how many rooms there are, and so on. So now we want to expand this idea, this very simple idea, this line, to more dimensions. So these are our data. We're going to have many features that I'm labeling on the bottom with 1, 2, up to n. And for each line, which represents one data that we possess, one house, we're going to have the price of the house associated. Okay. And this way up to d minus 1. So I'm start counting from 0. So in total, we have d data in our data set. This is the updated model that we're going to use. It's just a bigger line. So we have our usual constant term in front of it. And then we're going to have our features here. And before the features, we're going to have another parameters that we can tune. Okay, so all the a's, we choose them to reduce and minimize the cost function. Now we can write this in a kind of neater way. So I can call I can put all the a's into a vector here, and so I can do with all the x's. But you already noticed something, right? There is one extra a compared to the others. So in this case, we're going to have n x's, but we're going to have n plus 1 a's. So what I can do is that I can cheat, and in my vector of x's, I add a 1 in front of it. Okay, this is a kind of standard thing that people do. And at this point, I can write my model quite easily, like my y is equal to the dot product between my vector of a's and my vector of x. The dot product is basically I'm taking the product of the first element of the 0th element with the 0th element plus the first element times the first element times the second element times the second element and so on. Okay. This is just, let's say, a more compact way of writing everything. So now the question is, what's our cost function for our new updated multidimensional linear regression? You can scan the code and try and have a guess. And I can try to show the guess on the screen, although that's might not happen depending on my skills. So let's do it like that. Let's do it like that. Oh, that's actually working. But you can see the options now, right? Amazing. So what am I going to do? Should I switch? Okay, I'll let you go for a bit, and then actually I'll do one thing. I'll put this on my side so I see how things are going. Okay, I would say I will stop at 20. Well, guys, you have no doubts. So the answer is quite clear. The second option was actually, let's say, the right one, the one we're going to use. This one, I basically made it up. This is this is sometimes used, okay? But for now, we're just going to extend our previous cost function and let's say go with it. So this is the one we're going to use. So recap, for the multivariable linear regression, we have our model that is defined by a product of our features and these coefficients A, where we remember we add an extra 1 in front of our x. And this is the cost function that we're going to use. So again, you minimize this cost function using an optimizer. And if you come to the next workshop on Saturday, we're actually going to see how to do this in TensorFlow. That's great. Okay, let's discuss a last thing about linear regression. So let's say that we have two features, okay? The first feature tells us the number of rooms. We're going to have now 1, 2, 3, 5 rooms, and so on. The second feature is going to tell us the surface of the house. It might be 50 meters squared to 100 meters squared. No, that's something about that. You can immediately see that there is a mismatch between these two quantities. Can anyone tell me what's the issue? Yes.
Is it 5, 6 data for?
That's a good guess, but that's my fault. I should have probably put 6 data in the bottom circle as well. So how do they differ? So we can see that the number, first of all, the second group, X2, has units, right? So we may think, okay, what happens if instead I choose to express it in, I don't know, centimeters squared? Would anything change? Probably not. But anyways, that's kind of the mismatch. The first group of numbers for the feature 1 are all of order kind of 3, 5, right? Tens, anyways. For the second feature, the numbers are much larger. Now, we may think that that's completely irrelevant, that as long as our model finds the right coefficients A, that it's going to work. It's going to work anyways. However, turns out that it is true, but it is sometimes harder for the optimizer to find the minimum when our data are so different, right? So in particular, so this is the parameter space, the coefficient space. So this is going to be A0. This is going to be A1. And the thing that you see is the cost function. Okay. So the claim is that it's easier to go down on a ball-shaped cost function than it is to go down to a cost function that is kind of elliptical in the parameter space. Because now the claim is that here you're going to bounce up and down, up and down, up and down, whereas here you're going to go straight through the heart of the ball. And it turns out that if our data are so mismatched, it's more likely that we end up in this situation here, okay, where our cost function is not very regular in the parameter space. So we need to fix that. And this process is called normalization. You're going to see a lot. Normalization is always done. It's nothing bad. We're just trying to do so that all our features have the same mean and that they have the same standard deviation. Okay, what does it mean for the data to have the same mean and the standard deviation? So for instance, all our data are distributed around 0, and we don't have one feature that is kind of, it's about order of tens, and one feature that is the order of thousands. Okay. Well, you may think, what's the meaning of having minus 0.5 rooms in a house? It doesn't have a lot of meaning, but we can always, okay, well, actually, the trick that we're going to use is basically, given a feature, for instance, the number of rooms, we're going to calculate the mean of the feature, and we're going to find the standard deviation of our feature. And then we create, so if x1 is the actual number of rooms, we're going to create this alternative x1 that is defined by subtracting from every piece of data the mean and the standard, and dividing everything by the standard deviation. Of course, having like minus 0.2 rooms have no meaning, but using this formula the other way around, we can always come back to the actual number of rooms. Okay, so we're just transforming our data so that our model, it's easier to train. And this is called normalization. And again, this is something that we will cover on Saturday during the workshop. Now, just to spice things up, we can also think and represent linear regression with a nice diagram. So this is our usual linear regression. So we put our inputs in balls, and we connect the balls with another bigger ball. And this connection means that here I'm summing all the features weighted by the parameters A0, A1, A2, and AN. As usual, we shouldn't forget to put the fake x here, which is equal to 1. X0 equal to 1. Now, that was it about linear regression. Do you have questions? Yes.
Could you give an example of this? This is surface and the
Yes, I think that was not very clear the way I put it. So the lines, the ripples that you see are the contour of the cost function. A contour means that the cost function has the same value along those lines. So along the red, the cost function is going to have the same value. Now, your aim is getting to the center of these circles, okay? Because that's where you have the minimum of your cost function. And the claim is that if your cost function is not very symmetric, let's say in your parameters, like this case, the optimizer is going to it is going to take more steps for the optimizer to get to the center. So I like to stress it again. These things are the parameters A0 and A1. They are not the features. They're not the features. Okay. So we're plotting here the cost function as a function of the parameters. Any other question? Yes? Okay. So should we? So the question is, should we try using different starting values in the function to see if there are any dips? For instance, temporary dips and then lower minimum. Second question is cardinality, I think. So I don't understand the cardinality part. Maybe could you elaborate the question a bit more? But the answer is sorry, yes. That was okay. Sorry, yes, cool. Yes, indeed, it's a good idea to start from. I think you meant here, right? instead of starting from one place and try to get down, why not to try, and take many random possible initial values of A0 and A1? And I think that's indeed what some types of optimizers do. So they have an approach like, let's try many values. Let's try and let's see the one that brings me to the lowest. To the lowest. Maybe I'm going to end up for each of them. Maybe I'm going to end up in a local dip, but maybe then I can choose the one that is the lowest. Not like that. That's what I meant when I'm saying that these optimizers are actually smart. Okay, they're not just going down the cost function. Also, some optimizers, when you end up in a local minimum, they actually can get out of the local minimum because they kind of have a chance of doing a jump, which brings them outside from the minimum. So there's lots of optimizers, and choosing the right optimizer is also something that is important when you have a model. Let's go back to our here. Other questions in the chat? Okay, so let's move on the next topic, logistic regression. So logistic regression is used to do, so we said supervised learning had two possible tasks. One was kind of predicting prices or kind of predicting numbers. Distinguish a cat from a sandwich. Okay, so how does this work? This is an empty slide. Okay, so this is a sum up of the previous stuff. Sorry about that, I mixed up. So let's go through this quickly. So we started with our data set of many features, a number of rooms and stuff like that. And for every row, we had the price of the house that was associated. Then what we do is we normalize data. We normalize data so that it's quicker to train our model. So that we don't have the surface, which is 200, 300, and then the number of rooms, which is 3, 4, 5. Okay. Then once we have our data normalized, we start using our model. Note that the normalization is not just true for linear regression. It's always performed. We have our model where we have basically it's a line on many dimensions. We need to define a cost function because we need to find a way of saying, are these values of A0 and A1, or generally this vector of coefficients here, is it a good vector? Does it represent my data? So we need to do this cost function here. And then we need to choose an optimizer that kind of tries to find the best values of A0, of our vector coefficients A, where the best value really means the one that gives the lowest cost. And finally, usually what we want to do is we want to evaluate our model on a new set of data that's clean, and we check, well, is it working well? Is it not working well? Okay, now we go back to logistic regression, and we go forward to the actual slide. So logistic regression basically wants to draw a boundary between two possible types of classes. They're called classes. We have the red class here and the blue class. For instance, we could think maybe we have an engine, right? The one of a car, and we know two things about an engine. I don't know what you can know about an engine, but no, you could have one feature X1 and one feature X2, right? And then you have many engines. You can plot the engine with each of these data is an engine, and maybe you have some engines that don't work and some engines that work. And then once you plot them, you start seeing, well, it seems like there is a division between the two. It seems like I could be able to actually predict if my engine is going to work, just given these features X1 and X2. Okay. So our aim is, given the values X1 and X2, we have some function here, some function, and our output, we want it to be a probability distribution. So it's a value that is between 0 and 1. And if it's 1, it means that our engine is going to work. If it's 0, it means that our engine is not going to work. So maybe we could produce a new engine in the factory, and we could ask ourselves, are we actually going to sell it? Is it going to work? And then we'll have our model, and we'll see, okay, well, it's a good chance. There is a good chance that this engine is going to work, so I'm going to sell it. Otherwise, maybe I would need some more tests. Now, we may do that using logistic regression, right? But what's the problem with logistic regression? You have an idea about what the problem could be? Yes? Yes. So you could get values that are not 0, that are not between 0 and 1, right? Is that what you said?
No, if something is in between 0 and 1, how do you decide?
Well, you can say if it's above 0.5, then it's going to be it's going to work. If it's below 0.5, it's a probability, right? So you're saying that 0.5 means 50% it works, 50% it doesn't work, right? So then you could say maybe if the probability is higher than 0.8, I'm going to sell my engine. If it's lower, then I'm not going to sell it, okay? Because it's too risky for the customer. I could think something like that. But the true issue with logistic regression is that our value is a line. Okay, so I can take values that are from minus infinity, right, to plus infinity. Whereas what we want here is a probability that is constrained between 0 and 1. Okay, so that's why linear regression is not good, because the output is not what we want. So, and this is the thing. So we want to predict a probability that is either 0, which is 0%, or 1, which is 100%. So 100% chance that my engine is going to work. And the linear regression gives us a value that basically is unconstrained. Okay, according to the value of x here, I could get something that's very large or that is very negative, for instance. So one trick to do that is that we take the output of our linear regression and we apply another function on top of it. And this function is this function here on the bottom. And why to choose this function? Because this function is going to send very high values out of the linear regression to 1, and it's going to get very negative values of the logistic regression to 0. So the x-axis here is the output of our logistic regression. Okay, so we take the output of our logistic regression, we plug it inside this function 1 over 1 plus e to the minus x, and you see when the value of the logistic regression is 0, we're going to have 50-50 chance that our engine is going to work. Now you might think, why are we choosing this particular function? No, I could draw something that is like this. It's slightly different, but still kind of has the same properties, and that's true. You could, but no. Why not to go with this one? So basically, yeah, I cannot justify to you why exactly this one is chosen. There are other options. I think the arctan is another option, if I'm not wrong. But yes, let's go for this one for this lecture. So this is going to be our logistic regression model. Okay. As usual, we are going to have our engine features that are going to be here. I'm going to get these features and put them into our linear regression. So I'm making up new coefficients, A, and I'm multiplying each of the data that I have for a single engine with A1, A2, A3, according to how many data I have. And the result, I'm going to put it inside this function that is called sigmoid function. And I'm going to get from my features, from one engine, I'm going to get a value that is between 0 and 1. And this is kind of what I want, right? So that's about the model. So we have the task, predicting if the model is going to work, if the engine is going to work. We have a model that is just a linear regression with a function applied on top. And now we need to find the cost function. So is our model performing good? Is our model not performing good? You may say, well, why not to use the usual thing that we had for the linear regression, right? So for the linear regression, we had our actual label. So in this case, our label just tells us, is the engine working? So it's 1, or is the engine not working? So it's 0. And this would be the output of our model. There's a value, again, between 0 and 1. However, it turns out that this function, this cost function, is not very nice. So it is said it's not convex. So this is kind of a very, very sketchy diagram. So basically, the fact that it's not convex, it means that it has a lot of local minima. And that's really not ideal, right? Because when you're going to minimize it, you're going to get stuck here. And maybe with a lot of struggle, you're going to get out of the minima. Maybe you're going to get stuck here. So we don't really want to use this function. We would like to find something else that is representative of whether our model is predicting things well or not well. Now, who has heard about likelihood? Okay, a few people. So likelihood basically is a value that tells us how likely is basically how likely is it to get our data given the coefficients, if I'm not wrong. Might be the other way around, actually. Yes. So if you want, I'm going to put the slides later, and you can follow this link, and it actually gives an explanation of this approach. But basically, we can get this horrible thing that is a cost function. Now, there are lots of terms in here. We can try and break this down. So if you look at the inside of this horrible object here, so if we look at this thing here, which is, again, this one, basically we're saying that. So say that the engine is working. Okay, so yi is equal to 1. If this is our prediction from the logistic regression that we said takes values from 0 to 1, this is the value that this thing is going to get. Okay. So if the engine is working and we predict that the engine is working, this thing is going to be equal to 0, which is nice, right? Because it means that when I do find the right thing, I'm not adding anything to the cost function. When, on the other hand, we get probability, a very low probability that the engine is working, so that basically contradicts what's the actual fact, we're going to get very, very large values out of this object, this yellow object here, right? So I'm basically saying that if the engine is working, I'm going to have a high cost if I predict that the engine is not working. And similarly here, if the engine is not working, if I predict that the engine is actually working, I'm going to get very high values. If I predict that the engine is not working, I'm going to get 0. And 0 is fine, right? Because I'm not adding anything to the cost function. So it means that I'm doing a good job. Now, again, this really looks like out of the blue, but you can derive this formula, and you can find the derivation here in this link that I put. So if any of you wants to actually see how we got there, it's not hard. It requires some derivatives, but that's about it. And cool. Yeah, let's give a look to a last thing. So the decision boundary. So how do we know that? So we call the decision boundary when our prediction is 0.5. So 50% that the engine is working, 50% that the engine is not working. Now here, when I drew the data, I drew a line separating these two. How do we know that this is truly a line, right? That's a good question. It's a logic question that we can ask. Well, we start with our logistic regression that looks like that. Here we have our linear regression, and then we plug it into the sigmoid function, and this is overall what we get. Now we say that decision boundary is when this thing is equal to 0.5, so 50%. So you see we have a 1 here, we have a 1 here. 0.5 means 1/2, right? So it means that this thing needs to be equal to 1, which is what we're writing here. Now if we take the log on both sides, we're going to get the minus a dot x is equal to log of 1. Log of 1 is equal to 0. And this thing, a transpose times x, is just equal to our linear regression, right? So we have a naught plus a1 times x1 plus a2 times x2. In this case, we only have 2 features. And we have that has to be equal to 0. Now, if I rearrange the terms, I get that x2 is equal to minus a1 over a0, x1, minus a2 over a0. Okay, so this is indeed the equation of a line. So this is showing us that the decision boundary, which is where we are saying, okay, I have a higher chance of the model working, or I have a lower chance of the model working, is actually a linear decision boundary. Now, any question on this stuff? Yes. That's a good question. I don't know at the moment. Like, I think that's happened a lot. I don't know. I guess you can try to use some probability sampling to kind of assign, kind of fill the gap with a data sample in a kind of logical manner, and something is not too unreasonable. But the truth is that I don't know. Maybe you can have models that are capable of fitting your data even if they're incomplete.
But the question about like missing data.
Yeah, I think so. Was it like if you have a house?
Yeah, so if you have a house and then
So like you have like blanked out. Like,
yeah, exactly. So imagine you missed like surface area.
So what we typically do, this is called like imputing data. So when something is missing, you can actually like kind of assign maybe the mean value of something so hopefully it wouldn't like impact the model too much. Or you could use the other value to try and predict what that value would be. So this is called imputing. It's when we go to scikit-learn, the Python package scikit-learn has good functions and modules for it. Yeah.
Other questions? Yes.
With the cost function for 2 variables, you get local minimums. How do you avoid pulling into those and finding the optimal function?
So I think generally you don't avoid. You are going to fall into the local minima. But then your optimizers, so the optimizers are the algorithm that perform the update of your parameters, are usually quite smart. So even if they fall into a local minima, they don't give up. They start trying to look around it. And for instance, imagine this thing as a valley. What happens if you walk a bit out of the valley? Are you going to get to something that goes down, right? So they keep searching around, even if they're in a local minima. And hopefully you're going to get out of the local minima and keep going down the function. And as someone suggested on Teams, you can start from many different random positions of your landscape, right, of coefficients. And hopefully you're going probably to pick the one that's going to give you the lowest value. I don't think you ever get to the absolute minimum, maybe you do, but as long as it's performing, your model is performing good, that's good, I would say. Good question. Yes?
Is it possible to have access to this power?
Is it possible to?
Have access to this power?
Yes, I'll put it. Yes.
I understand that like graphs below.
Can you tell me what? Okay, so this was probably the hardest part. Like it's very mathy, and I just showed you this horrible equation. So this is the cost function, right? And here we have an index that is summing through all the data in our data set. So we start from 0 to d minus 1. D minus 1 because we're starting from 0. It's just a matter notation, right? And for each data, we compute this value here. Okay, that I also wrote here in yellow. Now, we have the the y is going to take a value either 0 or 1, because either the engine works or it doesn't work. And this is a piece of data, right? So it's not going to be 0.5 because I tried the engine, does it work? Yes, I'm going to assign the value 1. It doesn't work, I'm going to give it the value of 0. Now, if it doesn't work, this is going to disappear. I'm just going to be left with this term here, right? Because y is equal to 0, because it doesn't work. So this is what I have. And if I plot it as a function of, let's say, z, there is this thing here, I'm going to get this function. So, well, this was a lie. That was a lie. That is this thing here. Also captures this G here. So what I'm saying is that if my logistic regression is predicting a value of 1, okay, so if this is my logistic regression, so what I predict, if what I predict is 1, then that's quite bad. I don't want that to happen. I want to predict that it's 0. So I'm going to tell the computer, hey, this is very expensive. I'm going to give a huge extra value to your cost function. So now you're going to be very sad. You're going to try to reduce that. Whereas if I predict very well, I'm going to say, good job, computer. This piece of data is going to give added to the cost function a value of 0, because you actually predicted that the engine was not working. And I do this for every piece of data, and I take the total, right? And what I'm trying to do is try to make as many data happy as possible, right? So I try to reduce the value of the cost function by trying to accommodate every piece of data. Like, as you can see, we don't always do a good job. For instance, here we have a red dot, so an engine that is not working on this side of the decision boundary. And here we have a few engines that are working, and we're actually discarding them. And again, if you want to see exactly where this formula is coming from, I suggest you this reference on the bottom. It's like 1 page max, I think. Other questions? No questions? Okay. In the chat, of course. So doesn't that polarize the results? So is there any way to make this normal? Is there any way to make this normal for wrapping the result of the linear regression? So what do you mean with normal? Yeah, the sigma function here, right? Normally distributed, so fair. So the thing is that so your features x1 and x2 are usually going to be distributed themselves around some values. For the example of the house, we said that the number of rooms was already distributed around some value. Okay. So the reality is that I don't expect my linear regression to output values which are super large. So I don't know. I should think about that. I don't know on top of my head. Sorry. Other questions? I don't think so. So if you want, you can come on this Saturday on here, I think in the opposite room, right? Yeah, so opposite room from this one, from 11 to 1, we're going to have a workshop on actually how to implement all this stuff we talked about in TensorFlow. And if you want, we can have a social. Are we having a social at the union? Okay, probably we're having a social at the union after that, so from 1 onwards. So yeah, if you have any comment, if you okay, actually that was too rushed, that was too muchy, feel free to send an email and give some feedback. It's always very welcome.
We're on the cafe.
I'm not sure.
You're